Okay, so let's go ahead and get started. So far in this class, we've used our understanding of the representations of the Lorentz group to construct wave equations that are obeyed by particles with spin. And we studied at least a little bit the classical solutions of the free wave equation describing a particle with spin. And today I want to use this to begin our discussion of the quantization of the Dirac field. In particular, the quantization of this spin 1/2 field that describes a particle that has spin. Okay. So let me just remind you of where we left off last class. So a particle with spin, and in particular a free particle, so a particle with no interactions, is going to be described, at least classically, in terms of a 4-component spinor field. That is to say, a complex spinor field. So instead of 4 complex numbers that we could call psi a of x, where a is an index that runs from 1 up to 4, but typically we'll suppress that index and just call it psi, which classically obeys the Dirac equation. So I gamma mu d by dx mu minus m psi is equal to 0, where the gamma matrices are 4x4 matrices, which we've already spent a little bit of time studying in this class. They can be most efficiently written in 2x2 block form, as I have done here, where sigma mu is a 4-vector containing the Pauli matrices, and sigma bar is just a set of a notation describing a different 4-vector with a relative minus sign. So this is an equation of motion. And a general solution to this classical equation of motion can be expanded in terms of a basis of plane wave solutions. And we will consider the expansion in terms of these plane waves. So just as in the quantization of a classical field, we begin by imagining the solution of a Klein-Gordon equation expanded in terms of a plane wave basis. And then when we quantize the field, we promote phi to an operator, and we promote the terms that appear in this expansion of phi in a plane wave basis into operators that act on a Hilbert space. In the case of the scalar field, these were the creation and annihilation operators, operators that either create or destroy a particle. Similarly, as you can probably anticipate, we're going to write out the plane wave solutions of the Dirac equation. Imagine expanding a general field in terms of this basis of plane wave solutions. And then the coefficients will be raising and lowering operators, creation and annihilation operators that will either create or destroy an electron or a positron, say. Okay. So that's sort of where we're headed today. A lot of what I'll describe in the first part of this class is just a sort of summary of the free particle solutions, the propagating wave solutions of the Dirac equation. But then when we try and quantize this theory, we're going to discover that something sort of strange and miraculous happens, which is related to the fact that electrons have fermionic statistics rather than bosonic statistics. Okay. So, but to begin, let me just remind you of what these plane wave solutions looked like. So a general solution will look like, say, e to the I p dot x. And here I'll look for a solution that has negative frequency. So it looks like e to the minus I p dot x, where p0 is chosen to be the positive solution of the equation p squared equals m squared, i.e. p0 is the positive solution of p0 squared is the square root of p vector squared plus m squared. So these will be the positive solutions to the positive frequency solutions to the Dirac equation. And in a few minutes, I'll write down a set of negative frequency solutions. So last class, we argued that there would be two linearly independent solutions of the Dirac equation, which I'm going to label by an index here, S. So S equals 1 or 2, and S labels the two linearly independent solutions of the Dirac equation. And if we wanted to go ahead and find out explicitly what those solutions look like, all you would need to do is write out the Dirac equation in this plane wave basis. So you imagine acting with this differential operator on this guy right here. And what you'll see is that that turns into the equation. You just stare at it for a second. The derivative hits this x here, and it brings down a factor of IP, which is contracted with a gamma matrix. The gamma matrix is this off-diagonal guy that has sigma and sigma bar in the off-diagonal components. So the Dirac equation, written as a matrix equation, acting on the four-component spinor U, will take the form that I've written here. So here U is one of our two four-component spinors, and it just has to be a zero eigenvector of that 4x4 matrix that I've written there. And so finding the eigenvectors of a matrix is not hard to do. Finding the zero eigenvectors of a matrix is not hard to do. So for example, last class we worked out explicitly the case where the particle was at rest. So for example, if P is at rest, then this matrix was just proportional to -1, 1, 1, -1. And so U, the two solutions, just took the form of a four-component spinor, which is a two-component spinor zeta and another two-component spinor zeta on top of one another. Okay, so that's annihilated by the matrix -1, 1, 1, -1, where zeta is any two-component spinor. Yes? Sorry, this is at rest. Oh, yes, and there's a square root of m out front. Good. Thank you. So yes, if that's not obvious, just work it out. So let's work it out just to convince ourselves. So if our particle is at rest, then P is the 4-vector whose first component is m and whose other components are 0. And sigma 0 is just the identity matrix. And so when P is equal to 0, what does that equation become? It becomes m times -1, 1, 1, -1, acting on U is equal to 0. And if you just plugged in that right there, you would see that indeed it is annihilated by that matrix, because zeta plus zeta, zeta minus zeta is equal to 0. And that square root of m is just introduced for some sort of future convenience as for how we're normalizing this basis of solutions. So what I'm doing here might seem like a bit unfamiliar, but if you remind yourself of the theory of electromagnetic waves, hopefully it'll be a little bit more familiar. Remember, an electromagnetic propagating wave solution of Maxwell's equations looks like an oscillating plane wave factor times some polarization vector. And sometimes we even call these basis of U's the basis of two possible polarizations of a spinor. And of course, there are many different bases that we could choose. So for example, we could choose a basis of solutions where, say, zeta 1, where S is equal to 1, could be 1, 0, and zeta 2 would be 0, 1. This would be something like a linear polarization. So the two polarizations of the spinor would, at least in the rest frame, describe a spinor which has polarization spin up pointing in the z direction, and the other is spin down pointing in the z direction. But you're always welcome to choose some other basis of polarizations. So in a second, I'll describe to you what's known as a helicity basis, which is sort of analogous to the circular polarizations in electromagnetism. But by and large, you could choose whatever basis you like to make life convenient, and the actual choice won't really enter too much in our calculations. Yes?
Just a quick question. U sub S is a 2 by 2 matrix whose columns can stack together?
Yes, U sub S is a 4-component vector, right? So psi is a 4-component vector, or I shouldn't call it a vector because vector implies Lorentz vector in your head. So I call it a 4-component spinner. So U is a 4-component spinner, and it is annihilated by a 4 by 4 matrix, which is this matrix right here. And if I write it in 2 by 2 block form, so I think of the 4-component spinner U as a 2-component spinner on top of a 2-component spinner. 2-component spinners are the things that you kind of are used to dealing with in non-relativistic quantum mechanics. Then what does U look like? Well, it's annihilated, if I write it in 2 by 2 block form, it's annihilated by that matrix right there, at least in rest frame. And so then you can just write out what the two, you can easily convince yourself that there's a 2-parameter family of a 2-parameter family of 4-component spinners U that are annihilated by that matrix. And I've written them down here. And S here is supposed to be an index that labels the 2 linearly independent spinner solutions. Good. Hopefully this is all more or less clear. If it's not crystal clear, don't worry, because on the problem set that you'll be doing for next week, you'll be solving this equation, in particular this equation right here, to write down the generic solutions with arbitrary momentum, not in the rest frame. And the general solutions, it's quite easy. You're just solving this matrix equation. And I even give you some hints how to do it in the problem set. In fact, I think I write down the answer. Well, if I don't in the problem set, I'm going to write it down right now. So the general solutions take the following form. So you just take your favorite 2-component spinner zeta, and you act on it with the matrix, the 2 by 2 matrix, P dot sigma. Okay, remember sigma is so here, P dot sigma is otherwise known as P mu sigma mu. Sigma mu is the set of 4 2 by 2 matrices. You contract with P to get one 2 by 2 matrix. And here I'm taking the square root of a 2 by 2 matrix. What do I mean by the square root of a 2 by 2 matrix? The square root of a 2 by 2 matrix is the matrix you square to get the thing you took the square root of. Okay. Right? In particular, if you want to think about it a bit more explicitly, if you imagine a diagonal matrix, then the square root of a diagonal matrix is found by just taking the square root of all of the diagonal entries, the square roots of all the eigenvalues of that matrix. And so as long as you have a matrix that's diagonalizable, you could always go to a basis where it's diagonal, take the square root that way, and then go back to your favorite basis. So this is what the general solutions of that equation look like. Okay. So that's an exercise on the problem set that I just handed out. Just as a check, just consider the case where you're in the rest frame, so P vector is equal to 0, so P0 is equal to M, and then you'll see that this equation here is just exactly the same as this equation that I've written up there. So that's just a generalization of this. And really, any basis will work, so any choice of 2-component spinner zeta will work. So for example, I could choose this basis that I've written up here. But more generally, just to keep the normalizations relatively simple, so we will just choose a basis So we'll choose two spinners, zeta 1 and zeta 2, such that the spinors, these two component spinors are orthonormal in the sense that if you took zeta dagger, zeta 1 dagger times zeta 1, that's equal to 1. Zeta 1 dagger times zeta 2 is equal to 0. Zeta 2 dagger times zeta 2 is equal to 1. So for example, that is exactly the property obeyed by those spinors up there. Okay. That's just some choice. So I'm choosing my spinors to be orthonormal. I'm putting a dagger there instead of a transpose, just because I want to allow, in general, these things to be complex, because spinors can be complex. But essentially, this means that we have an orthonormal basis. And then you could choose your favorite orthonormal basis and write out these spinor solutions explicitly. So let me just give you one more example. So let's, rather than taking a particle at rest, let's consider the example of a particle which is just moving in the z direction, just for the sake of simplicity. Of course, you could always, if you have a particle, you could always go to some frame where it's moving in the z direction. That's just a choice of what you call z. Then what is the matrix P dot sigma? Well, sigma 3 is proportional to the identity matrix. Is a diagonal matrix whose entries are 1 and minus 1. So this is just E minus P3, or the square root of E minus P3, and E plus P3 on the diagonals. How do you see that? Well, first write down the matrix P dot sigma. So E here is P0. So it's the square root of P3 squared plus M squared. P dot sigma is the matrix with diagonal entries E minus P3 and E plus P3. And to take the square root of a diagonal matrix, you just take the square root of the diagonal entries. And so then this basis that I've written down above would then be given by, for example, say U1, which would be a spinor. So all I do is I just take these matrices here, and let's act on the matrices zeta 1 and zeta 2, which are 1, 0, and 0, 1. So it's given by, so if, for example, we took zeta 1, sorry, I guess I'm using a subscript there, to be 1, 0, then U1 would be the square root of E minus P3, 0, and the square root of E plus P3, 0. All I'm doing is acting with P dot sigma and P dot sigma bar on zeta 1, and then zeta 2 would be this guy. So U2 would be 0, the square root of E minus P3, 0, and the square root of E plus P3. And so the first of these is a spinor which has spin in up, spin pointing in this plus z direction, and this guy would describe something, a particle, which has spin pointing in the minus z direction. Is this all clear, more or less? Okay. At this point, what I might do is just introduce a little bit of language. It's not language that I'm actually going to use in this course, but it's something that people use all the time. So I just want to explain it so that you're not confused when people talk about this. So sometimes when people talk about spinors, they characterize spinors not in terms of their polarization, but in terms of what they call their helicity. So the helicity of a spinor is its spin pointing in the direction of propagation. So, in particular, you could always imagine having a spinner here, a spin 1/2 particle, and measuring its spin in the z direction or the x direction or the y direction or something like that. But if you have a particle that's moving with some momentum or some velocity, then a natural thing to measure is not its spin in the z direction, but its spin in its direction of propagation. Okay. In particular, this is the eigenvector of the operator that we could call H, which is P. So that's what we would call P hat. Okay, so P vector, where we remove the normalization, where we normalize it to be 1, dotted into the operator that measures the spin of a particle. That's the thing that we would call Sij. Okay, so it would be S12 to measure the spin in the z3 direction, for example. And what is that operator? That's an operator that we've worked out twice already, I think, in both of the last classes. So it would be the 4x4 matrix acting on these 4-component spinners, which in 2x2 block form you would write as sigma 0, 0, sigma. So a couple comments are in order when I use the word helicity. The first is that the helicity of a particle, at least of a massive particle, is not a Lorentz invariant concept. In particular, you could have a particle that's moving in the plus z direction, but then at 10 miles an hour, or kilometers an hour, I suppose. But then you could go to a frame that's moving in the plus z direction at 20 kilometers an hour. And then when you go in that frame, the particle looks like it's moving in the minus z direction. So something that looks like it has positive helicity in one frame could look like it has negative helicity in the other frame. Okay. So this is a concept that depends on a choice of rest frame. But once you choose a rest frame, okay, you build your particle accelerator. You're not going to be putting it on any trains anytime soon. Okay, so you choose a rest frame, and then the notion of helicity is well defined. Okay, so for example, this guy here, instead of saying it has spin in the plus z direction, you could say it has positive helicity, and this guy you would say has negative helicity. So I'm not actually going to tend to use much of this terminology in the class. Generally speaking, when we compute things in quantum electrodynamics, say, in terms of these spinners, I might just say, consider a spinner whose polarization is blah, okay, rather than talking about helicity. But it's a terminology that is used somewhat frequently. Are there any questions on this before I continue? I mean, the terminology can get sometimes a little confusing because we talk about sometimes the helicity of an object, the chirality of an object, which is slightly different, and the spin of an object. These are all slightly different things. Okay. The spin of a spinner, well, okay. Okay. So those were the positive frequency solutions. There are also two linearly independent negative frequency solutions. So that is to say, solutions to the Dirac equation, which look like e to the plus I px, where here p0 is greater than 0 and is the solution of p squared equals m squared. And just as we did above, we could write down a general family of linearly independent solutions to the Dirac equation, now with negative frequency instead of positive frequency. what would these solutions look like? Well, there would be two of them labeled by an index S. And the form that they would take is very, very similar to the form that we've written above. There's just some minus sign that creeps into the calculation somewhere, as you'll show on the problem set, I believe. Minus. No, I've changed the sign here. Okay. So yes, yeah. So, when I say negative or positive frequency, that's slightly ambiguous as to what I mean. What I really mean is that here we had a minus sign, and here we had a plus sign. Good. Yeah. Have I reversed what I mean? Okay. Just as I can't really tell right from left. I can never really remember how we define positive and negative frequency. One of them goes like plus a positive number times time. One of them goes like e to the plus positive number times time. The other goes like e to the minus positive number times time. Yes. Good. So this is another set of solutions to the Dirac equation. And here eta sub s is another basis of two-component spinors. Which again we will normalize so that they are orthonormal, just as the zetas were. I suppose we could take the etas to be the same basis as we did for the zetas, but we don't have to. And these v's, along with the u's, describe a general solution to the Dirac equation. Okay. So every solution to, or let me say that even more generally, every four-component spinor can be expanded in terms of this basis of solutions, in terms of the u's and the v's. Okay. Just as every function of x can be written as a sum of e to the ipx and e to the minus ipx times some coefficients, that's the Fourier decomposition, that's Fourier's theorem. Every spinor can be written in Fourier space, where it just takes the form of a linear combination of this basis of plane wave spinor solutions. Is that more or less clear? And in order to understand this expansion, we're going to, one has to really study in a bit of detail this basis of plane wave solutions. So one of the things you'll do is you'll work out this basis of solutions, as I've indicated here, and you'll derive some properties. Okay. One of the properties that you'll derive that we'll use later on in this class, this lecture, is the normalization conditions. So the normalizations that the zetas are orthonormal, as well as the etas, translate into some normalization conditions for the u's and the v's. In particular, they translate into the condition that u bar times u is either 1 or 0, depending on whether r and s are equal, along with the normalization constant m, which is the square of that square root of m that I introduced earlier. And similarly for the v's, and finally, the u's and v's are mutually orthonormal, in the sense that u bar times v is equal to 0. Now here, remember that I'm using the bar rather than the dagger. So U bar is U dagger times gamma 0, as we defined last class. And so you will check these on one of your exercises. Straightforward manipulation of 2x2 matrices. And just as a check to convince yourselves that this is right, you can stare at this basis of solutions that I wrote down for a particle at rest. So where was it? For a particle at rest, this is what UR and US looked like. And you could just take U1, say, to be given by that guy, and U2 to be given by that guy, and then you could go ahead and work it out. Okay? And that's just some multiplication of calculating the inner products between these vectors. Okay. So we're now in a position to begin to study the quantization of the Dirac field. But before I do that, let me pause and see if there are any questions. So just maybe to set the stage, so if you've fallen asleep, you can now wake up. So the idea is that a general solution or a general spinner can be expanded so a 4-component spinner psi can be written in momentum space as an integral d3 along with some normalization factor. So this is just some convention, just that same convention that we used in the scalar field case. And now we have 4 different possible solutions to the Dirac equation with a given momentum p. And so we'll call the coefficients in this Fourier expansion APS. Okay, I guess I was using subscript there. And BPS dagger. So here, all I'm doing is I'm writing down the general expansion of an arbitrary 4-component spinner in terms of the basis of solutions that we constructed above. Okay. So there's the expansion for psi. And here, I've given suggestive names to the coefficients in this expansion. Okay, these are the Fourier components of the spinner psi. I've called them A and B dagger, and they're labeled by a momentum p, just as they were in the scalar case. And now they're also labeled by another parameter s, which tells you which of the spinner polarizations we're talking about. And there's a similar expansion for psi bar, which is psi dagger times gamma 0, which is just found by taking the bar of this equation here. So what do we get? We get a BPS times VS bar of P times e to the minus IP dot x plus APS dagger times US of P e to the plus IPX. Now, of course, when you're talking about classical spinners, A, B, A dagger, and B dagger are just names that you give to the Fourier components of a spinner when you write it in momentum space rather than position space. But to quantize the theory, what do? We promote psi and psi bar to operators. And that means that we have to promote A and B to operators. So the A's and B's will become operators. And just as in the quantization of a free scalar field, A, P, S dagger, what is that? That's the operator that creates a particle, that is to say a spin 1/2 particle, with polarization S. So S labels the two different possible polarizations a spinner can have. And Bp of S creates a different type of spin 1/2 particle. And I'm going to give that a suggestive name. I'm going to call it an antiparticle. Which also has spin S. So for a real scalar field, we just had one kind of creation operator that created a particle with a given momentum. For a complex scalar field, you had two kinds of creation operators, one that created a particle and one that created an antiparticle. For a spinner, we now have four kinds of creation operators, because you can create a particle or an antiparticle in either one of two possible spin states. You know, for say a particle moving in the z direction, it could have positive helicity or negative helicity. Spin in the positive z direction or spin in the negative z direction. Now, I haven't really proven to you that these are antiparticles. That the A's and B's create antiparticles of one another. In fact, I haven't really defined to you what an antiparticle means. What you can immediately conclude from what I've done here is that the A and B particles have the same mass. It will turn out that these particles also carry charge. And as we'll see, they're going to carry opposite charge. For the scalar field case, you worked this out explicitly on a problem set. You saw that particles and antiparticles had opposite charge. And we'll see it's a very almost identical calculation to see that the same is true in the spinner case. We'll do that later on in this class. But right now, you should think of it as just two different species of particle that have the same mass. Are there any questions before I continue? I'm about to, there's going to be, a thunderbolt from the sky in about 30 seconds. So let me just make sure that everything is clear before I continue. Okay, so here I've written my field. I've expanded it out in a basis of spinner polarizations. I have raising and lowering operators. Everything should proceed just as it did in the free scalar field case, right? That's what you would think. And if I wanted to, I could happily proceed for the next 30 to 45 minutes, repeating all of the calculations I did for the free scalar case in the case of this free spin 1/2 particle. But about 30 to 45 minutes from now, I would begin to discover that there are problems for this theory. In particular, I would discover, for example, that energies are unbounded below, that propagators violate Lorentz invariance, that it's possible to go back in time and kill your grandfather, all sorts of terrible things. Because it turns out that there's one sort of simple but incredibly important subtlety that we have to take into account when we quantize spin 1/2 fields, okay? Which is that we need to think about the statistics of these fields. And so what I want to do now is I want to give you a sort of brief discussion of the relationship between spin and statistics. Okay. So if I can spell it, the subtlety is that these particles should be fermions rather than bosons. So in order to describe what I mean by that and what the implications are, perhaps it's worth stepping back for a few minutes and thinking a little bit, or reminding ourselves a little bit of what we mean by the statistics of a type of particle. Okay. So in particular, so you surely learned about bosons and fermions in your lives before. So let me just remind you of exactly what we mean when we talk about a boson or a fermion. So let's imagine that you have two identical particles. So let's say that we have two identical particles. By identical, I mean that there's no experiment that we could do to distinguish between the particles. They don't have different color, they don't have different charge, they don't have different mass, anything like that. They're quantum mechanically identical. Then they would be described in quantum mechanics by a wave function that we could call psi, and this wave function would be a function of the positions of these two particles. Now, if these two particles are identical, then you would say that the wave function should not change if you swapped x1 and x2, okay, if you interchange the two particles. So, indeed, if that's the case, then we have a special name for that kind of particle. We call it a boson. So the defining feature of bosons is that when you interchange the two particles, you get the wave function back again. Indeed, if I were talking about if not a wave function, but some sort of classical probability distribution, so psi was the probability of finding a particle at x1 and another particle at x2, then the statement that they're identical particles is precisely the statement that psi of x1, x2 is equal to psi of x2, x1. But the important point in quantum mechanics, the really important point in quantum mechanics, is that the phase of the wave function is unobservable. So in quantum mechanics, the phase of the wave function is unobservable. So when I say that, psi of x2, x1 should be equal to psi of x1, x2, I really mean that any observable, anything that I could observe should be unchanged if I interchange the two particles. So in particular, that means it's also possible to have a type of particle known as a fermion, which have the property that psi of x2, x1 is minus psi of x1, x2. So that you pick up a sign every time you interchange two particles. Now, I've phrased everything here in terms of a pair of particles, but of course you can have n particles, and the statement that they're bosons is the statement that the wave function doesn't change if you interchange any two of them, and the statement that you have fermions is the statement that the wave function doesn't picks up a minus sign every time you interchange any two of them. And so far I've phrased everything in position space, but in momentum space we could just as easily write down the consequences of being a boson or a fermion. So for example, in momentum space, you could imagine a two-particle state with one particle of momentum p1 and another particle of momentum p2. You could write down a wave function in that basis. And then for bosons, if you interchange the two particles, you would get a plus sign. And for fermions, you would get a minus sign. So let's now think about the particles that we've studied so far in this class. So when we quantized a real scalar field, we used operators AP and AP dagger that commuted with one another. So that, for example, a two-particle state where you have two particles with momenta p1 and p2 is the same as the state where you have particles with the creation operators applied in the opposite order. Okay. So these particles were bosons. So the question then is, how would you construct a field theory where the particles are fermions instead of bosons? To get a theory of fermions, the operators that create or destroy particles must not obey commutation relations, but they must obey anti-commutation relations. So what does that mean in particular? What we require, for example, is that AP1 dagger with AP2 should not be 0, but that the anti-commutator of the two should be 0. So that, for example, if you took an operator, a state, where you first create a particle of P2 and then a particle of P1, then that is related by a minus sign to the state where you do those operations in the opposite order. Similarly, the lowering operators must anti-commute with one another, and the canonical commutation relation that AP commuted with AP is equal to 1 becomes the anti-commutation relation between AP and AP dagger. So, whereas in order to construct the theory of a free boson, one uses an infinite set of simple harmonic oscillators, one for each momentum mode, to construct a theory of free fermions, you use an infinite number of harmonic oscillators, but they're fermionic oscillators instead of bosonic oscillators. So the bosonic simple harmonic oscillator is something that you studied very well in your quantum mechanics class. You probably know its spectrum by heart, all its properties by heart. It turns out that the fermionic simple harmonic oscillator is also a system that you studied very well in your quantum mechanics class. It's far, far simpler than the regular simple harmonic oscillator. Turns out that the fermionic harmonic oscillator is just a two-state system. In particular, and this is something that you'll show on the problem set, a fermionic harmonic oscillator is just a two-state system. So it has a ground state. So if you just have a single fermionic oscillator, then you would have just, so let's call it A, you would have a ground state whose defining property is that it is annihilated by the fermionic lowering operator. And you have a single excited state which you might call the one particle state, where you act with a dagger on that ground state. And what happens if you try and construct a two particle state? Well, the two particle state a dagger squared acting on the vacuum, well, a dagger anti-commutes with a dagger, So A dagger squared is minus A dagger squared. A dagger squared acting on the vacuum is minus A dagger squared acting on the vacuum. So it's equal to 0. Right? The statement that A dagger anti-commutes with A dagger is the statement that A dagger squared is equal to 0. Right? So that means that there's no such thing as a two-particle state in the fermionic oscillator. And this is a principle that you know very well. This is, in fact, just the Pauli exclusion principle. Right? Two fermions cannot occupy the same quantum state. So, indeed, to obtain a theory of fermionic spinors, the A's and B's must be taken to obey anti-commutation relations. So, for example, all of the A's have to anti-commute with one another. The B's have to anti-commute with one another. And moreover, the A's and the B's have to anti-commute with each other. Okay, so for example, the A's, so I guess I wrote down the A's up here. The B's also have to obey the same algebra. And indeed, the A's and the B's. So here, let me just write it all out, including all of the spinor indices, just so that everything is crystal clear. So the A's have to obey an anti-commutation relation. Sorry, P1 and P2. The B's, and with a delta RS, okay, because those two spin states were linearly independent, the B's must also obey an anti-commutation relation with the usual conventional factors of 2 pi. And unlike the case of the scalar field where all of the other commutators vanish, in this case, all of the other anti-commutators must vanish. So, for example, the A's and B's don't commute with one another, they anti-commute. And this is really a definition, let us say, of what we mean by a theory of fermions. So, for example, what are the states of the theory? The states of the theory are, in fact, much simpler in the sense than the states of the real scalar field. Because for the real scalar field, you could have 2 particle states, 3 particle states, and so forth, even if the particles have the same momentum. The states of the spin 1/2 field, well, you'll have a vacuum state, which is annihilated by all of the lowering operators. And then you will have other states that are built on this by acting with raising operators. But you can only ever act with the same raising operator once. Okay. So for example, you will have a state and states that look like, say, A P1 dagger up to A Pn dagger, and B, let's call it Q1 dagger up to B Qn dagger acting on the vacuum. So this would be a state with, let's call that n particles with momenta P1 up to Pn, and m antiparticles with momenta q1 up to qm. And I should really be putting vectors symbols on everything. And of course, if any of the p1s is equal to any of the other pi's, then this state is just 0 because of the Pauli exclusion principle. Okay. So, if you like, you could just take this as part of the definition of what I mean by a theory of free spinors. You know, that we just declare that we must use anti-commutation relations rather than commutation relations because we're looking for a theory of fermions. But you could certainly ask what would have happened if we tried to use commutation relations instead of anti-commutation relations. And in fact, there's a very deep and important result in quantum field theory known as the spin statistics theorem. Okay. You know it's important because physicists don't usually call things theorems if they can help it. But the spin statistics theorem says that in 4 dimensions, that is to say, for Lorentz invariant theories in 3 space and 1 time dimensions, theories, particles with even spin, that is to say, with integer spin. So, for example, bosons, scalars, vectors, gravitons, and so forth must have bosonic statistics. And particles with half-integer spin namely spinors, must have odd statistics, so must have fermionic statistics. And what goes wrong if you don't do this? Well, in fact, 3 things go wrong if you don't do this. So the first thing that goes wrong is that the theory is unstable. So there's the energy, the ground state is no longer the state with the lowest energy in the theory. You can actually lower the energy infinitely in a way that you'll show on your problem set. Second, the theory is not Lorentz invariant. So the propagator one could construct, it turns out, is not a Lorentz invariant propagator. And finally, the theory is acausal. Okay. So you can go back in time. And all 3 of those problems disappear if you quantize these fields using the proper statistics. So, for example, you can look in the textbook, and one of the things that the author does is go ahead and try and quantize the spin 1/2 particle using bosonic statistics and gets nonsensical results. And the problem is that you're actually going to go through an easier exercise where you try and quantize a boson using fermionic statistics, and you'll show, one of the things I've asked you to show is that the theory is unstable. You'll see exactly why that's the case. And that just turns out to be one instance of a very powerful result that's known as the spin statistics theorem. I'm not going to try and prove the spin statistics theorem in this class. It's a rather, it's beautiful, but it's a rather complicated proof. And in fact, just sort of to whet your appetites, the proof is very special to 4 dimensions. And in fact, it involves the topology of the Lorentz group Okay. So the Lorentz group was the group of transformations of boosts and rotations in four-dimensional special relativity. And it turns out that the obstruction to the construction, say, of spin-zero particles with fermionic statistics involves the topology of this group. So it's a little bit sophisticated. But the reason why I bring it up is that it fails in lower dimensions. Now, this may not be interesting to you if you happen to remember that we live in 3 space and 1 time dimensions. But very often, if you're studying a material, say, that's confined to a 2-dimensional plane, then you would describe that in terms of some particles that live in lower dimensions. And indeed, not only are violations of the spin statistics theorem possible in lower dimensions, they're observed in lower dimensions. So in lower dimensions, the relationship between spin and statistics is much weaker than it is in higher dimensions. Roughly speaking, the way that you should think about this is that when you think about spin, you should think about what the constraints of the symmetries of the problem. So when I talk about spin, in 3 dimensions, rotation symmetries are generated by a 3-dimensional group of rotations. Whereas if you went down 1 dimension less, if you have particles on a plane, you only have 1 symmetry, one generator of rotations rather than 3. So you've lost some of the symmetries, and whenever you lose symmetries, symmetries are powerful at constraining the solutions to problems. When you lose symmetries, the world is your oyster because there are fewer constraints on the solutions to whatever physics problem you're solving. Okay. So for example, in 2 + 1 dimensional theories with 2 space and 1 time, one can actually have not just fermions and bosons, but also particles with more exotic statistics, known as anyons, or maybe it's anyons, okay, because I think it comes from the word any, but people always seem to pronounce them anyons. What are these? These are particles which have the property that they just pick up an arbitrary phase when you interchange 2 of them. Remember, it's only the norm of the wave function that's observable, so there's no reason why instead of plus or minus 1, a particle couldn't pick up e to the 2 pi I over 3. Okay. What is e to the 2 pi I over 3? It's a cube root of 1, so you would say those are particles with Z3 statistics. That's what you would call them. And in fact, in fractional quantum Hall systems, people have claimed to observe these in the last few years, maybe the last 10 years. Yes, there's a question. Is that right? Okay. Yeah. Yeah, it's a kind of controversial subject that I'm not an expert on, so I'll just say that there are claims. Okay. I don't know what the latest is at. There were claims as of 7 or 8 years ago. I don't know what the current status is. In fact, there are claims that they're anyons not just with these sorts of statistics that I've drawn here, but rather what are called non-abelian statistics. So these are things that, I don't know if is that what the talk was about?
Yeah.
This is the 7/2 state and the, what's that?
It was about mostly the 5/2 states.
Yeah, so there's the 5/2 state, which has some SU2 something. I don't quite remember. So there's even more complicated statistics that's allowed in the world. My understanding is that the non-abelian statistics is quite controversial experimentally.
Abelian statistics seem to be greatly accepted.
That's my understanding. Yeah,
Non-abelian and logarithmic.
those people who wish to construct quantum computers love these things with non-abelian statistics because it means that you can take particles and you can braid them around one another in interesting ways, and then the degrees of freedom in this braid are very robust against quantum corrections. Okay. Or that is to say, they're very robust. It's some sort of non-local behavior of the wave function, so it's very robust against decoherence, which is the thing that you worry about when you're building a quantum computer. So there's a whole field, what's called topological quantum computing, which is based on the premise that this may be a good idea. Okay. Right. So I'm not going to say too much more about spin and statistics in this class, but maybe before I end this discussion, I can pause and see if there are any questions. Yes.
So if you're in 3 dimensions, well, 3 space plus 1 time dimension, there is no other phase shift other than
Correct.
plus minus 1.
That is correct. That is correct. That is correct. You know, there's sort of a picture that you can draw to kind of intuitively convince yourself why it is you can allow a phase in lower dimensions and not in higher dimensions. So in lower dimensions, I mean, what's the best way to say this? Like, let's imagine that you have a particle here and a particle there. Okay. One way that you could go to, one way that you can think about these anyons is to imagine that if these particles are just confined in a plane, then you could imagine doing some sort of rotation to sort of interchange the 2 particles. Okay? And then you could imagine doing 2 rotations or 3 rotations or something like that. And then in 2 dimensions, the number of times you wind around is something that makes sense geometrically. But in higher dimensions, if you think about it, there's no way that 2 particles can wind around one another. So the statistics of anyons, the fact that they can have non-trivial statistics reflects the fact that particles, particle paths through space-time can have a winding number around themselves. So winding here is a topological characteristic of the paths that these particles take through space-time. They're literally wound around one another. But if you think about it in 3 plus 1 dimensions, there's no such thing as winding. Because you can take 2 particles in 3 dimensions, and you could say, well, they're wound here, but I could have also gone up on top or something like that. There's just no such thing as winding in 3 plus 1 dimensions. At least no such thing of winding of particles. You could have an extended object, like a 1-dimensional string, and you could take a particle and you could wind it around that. And that's a topological invariant, and there could be statistics associated with that. And indeed, there are theories where there are statistics associated with these non-local objects. Okay. So when we talk about gauge theories, we'll encounter some of these non-local objects. They're called Wilson lines or Tooft lines and stuff like that. Okay. They're used as observables that probe things like quark-gluon plasmas and Yang-Mills theories, things like that. We won't have occasion to talk about their non-abelian statistics, though, but that is something that's allowed. So you can sort of see, at least intuitively, why the topology, how topology comes into play with particle statistics. Yes?
And would this anyone then obey the Dirac or
Well, in general, in lower dimensions, the spin of a particle is not nearly as strongly correlated with the type of statistics. So I don't think it's determined by the statistics, as far as I know. That's actually something that I'm not entirely sure about. But as far as I understand, it's not determined. Certainly, I know if you even go 1 dimension less, you can easily construct theories where bosons have fermionic statistics. Spin 0 particles have fermionic statistics, and spin half particles have bosonic statistics. If you think about it, once you go down enough dimensions, even the concept of spin is not a sensible notion, right? I mean, in order to define spin, you need to have some directions to rotate in. Okay. If you take a bunch of particles on a line, there's no rotation possible. So yes. Yes?
Is there some kind of conceptual way of thinking about if you go to a higher number of dimensions, what would happen?
People certainly talk about that all the time. So for example, in 5 dimensions, you can have 2 strings that have winding number around one another, and you could have interesting statistics associated with that. There's a whole zoology of these things. Lower dimensional field theories are something that are of very important experimental interest, and so I like talking about them. Higher dimensional field theories are of formal interest, I would say, but not experimental interest as far as we know. So we probably won't really talk about them in this class. But yes, there are certainly similar things you can say. The interesting thing is that in higher dimensions, the constraints of Lorentz invariance become that much more powerful. Okay. In sufficiently high dimensions, the possible types of quantum field theories you can construct is carved down to practically nothing. Good. Excellent questions. Any more questions? Okay. So, just to summarize, we have a field operator psi, which is expanded in a basis of solutions. So here, I'm just going to write it out for you again. So we sum over polarizations. Times e to the minus I p dot x with a similar expression in terms of an operator that we'll call b p dagger. I guess times e to the plus ipx, along with a similar expression for psi bar. So here you would have a b bar times, sorry, a b dagger times v bar and an a dagger, sorry, a b times v bar and an a dagger times u bar. And these A's and B's are regarded as the raising and lowering operators that create or destroy fermions, and so obey anti-commutation rather than commutation relations. Now, of course, with malice of forethought, I've chosen to call these operators A and B with daggers in the right places. I could, of course, define some other operator C, which is B dagger, and written this as a C here. Then I would have discovered that one of those C's and a C dagger lowers energy rather than raises energy. So I've chosen the A's and the daggers in these equations appropriately so that they obey the sort of usual harmonic oscillator algebra, albeit with anti-commutation rather than commutation relations. So for example, we could then, given this, go ahead and compute the same sorts of things that we computed when we studied a scalar field. So, for example, we could compute the Hamiltonian How would we go ahead about doing that? Well, the Hamiltonian is the integral d3x of t0, 0, where T mu nu was the stress energy that you compute by, well, we compute it in the case of a scalar field, and the computation is very similar in the case of a Dirac field. And the answer that you get, I won't go through the details because I'll do another very similar computation in a few minutes, is exactly the answer that you would expect. So the Hamiltonian is given by a sum over all possible oscillator mode, all possible momenta P, along with all possible spin states S of, I guess, I can never decide whether to call it omega or E, so I guess I've been calling it E, times the energy of a particle times the number operator that measures the number of particles with spin S plus the corresponding number operator that measures the number of antiparticles with spin S. So S, B, S, B. So the operator A dagger A measures the number of antiparticles, of particles with momentum P and spin S, and this guy here measures the number of antiparticles. And these are the fermionic number operators just as they were in the boson. Just as A dagger A was the bosonic number operator. And indeed, you'll get some chance to work out the details of these fermionic oscillators on the problem set. I'm not going to go through the computation in too much detail because I think it's almost identical to the computation that I went through before. If I have time at the end of the class, I might go through a similar computation just for a couple minutes. Maybe before I do so, I should pause and see if there are any questions. So this is just the statement that a fermion with spin S and momentum P has an energy EP. So EP, of course, being the square root of P squared plus M squared. And with the exception of that sum over S, this is identical to the formula that we had for the free bosons. Any questions? And as usual, as you discovered, I think, on the problem set last time, one always has to worry about a total additional constant term to this energy. But one doesn't have to worry too hard because the total overall constant that you add to the energy of a system is unobservable. So we will typically just set that constant equal to 0. Just by deciding to normalize our ground state to have 0 energy. And one of the things that you'll prove on the problem set, well, you can see it immediately, is that this Hamiltonian has a positive energy density. The Hamiltonian of all state, the energy of any possible state in our Hilbert space is positive. And you'll discover that if you try and violate the spin statistics theorem, that is no longer true. Let me conclude with one final comment, which is that the spinner that we're studying has a symmetry. So the Dirac equation has a symmetry which reflects the fact that the Dirac spinner is complex. And so you could always multiply that spinner by some phase. And then the Lagrangian, which I remind you was psi bar times I gamma mu d mu minus m times psi, will be invariant. This is just like for the complex scalar field. And associated with that symmetry, there is a conserved charge. How would we go about computing that conserved charge? Well, the current, J mu, can be computed using a Noether procedure. I tried to make you guess what this current was last class, but you guys didn't do very well, so I think I'll derive it for you. So the current follows from a Noether procedure. So in particular, what is the current? Well, the current is the variation of the action, or the Lagrangian, with respect to, well, in general, it's with respect to the field times the variation of the field So what is the variation of the field? So the infinitesimal variation of the field is just proportional to the field. And what is the variation of the Lagrangian with respect to d mu psi? Well, that's just gamma mu psi bar times gamma mu. So the total current is just psi bar gamma mu psi. And the conserved charge what is that? Well, it's the integral d3x of J0, which is psi bar gamma 0 psi. In order to compute this, so let's just write this out explicitly in terms of our raising and lowering operators. So what do? Well, you just plug in, for example, our expression for psi as the integral d3p of a times a u times e to the minus ip dot x plus b dagger times v times e to the plus ipx with a similar expression for u bar, and you then use the normalization conditions and the orthonormality of the u's and v's that we worked out above, and you'll find an expression for q, which is the integral d3p over 2 pi cubed times the sum over s of AP S dagger APS minus BPS dagger BP. That's actually a calculation that I wanted to go through because I think it's useful. You know, we did this calculation essentially a couple times for the free scalar field. It's worth going through in detail at least once for a spinner. So maybe next time, if you like, I could either go through it carefully for the computation of the Hamiltonian or for the charge, or maybe I'll do it for the propagator. But I just want to write down this formula so that I can point out one thing, which is that the charge is the number of particles minus the number of antiparticles. So in order to go from this line up here to this line down here, one just needs to take this expression here and plug it in to this equation along with the appropriate expression for psi bar. You've got to muck around with those u's and v's a little bit, so you need to use those normalization conditions that we wrote down earlier. It's worth going through those calculations, so probably what I'll do next time, I mean, as in the scalar field case, all of these calculations are all sort of similar to one another. You don't need, so I'm not going to go through every single one of them in complete detail. Maybe next time what I'll do is I'll work it out explicitly in the computation of the propagator, and it's a very similar, almost identical calculation for either the Hamiltonian or the charge, as we wrote down here. Okay, so that is the quantization of the Dirac field. Let me pause here and see if there are any questions. Maybe I can take one more minute and just maybe give you a little context so that you know where we're going over the next several weeks. So next class, well, next Tuesday I'll be out of town, but as I said in my email, I've arranged a surprise guest lecture, so that'll be exciting. You should all go. But following that, I'll probably wrap up a few details involving the quantization of spinners. And then we've really exhausted the set of examples of free field theories, and it's time to start considering interactions. And this is where quantum field theory gets interesting, because we then discover the machinery of Feynman diagrams and scattering and all of that stuff. But before I do that, actually, I want to talk, I'm going to spend maybe a lecture or so talking more generally about the types of interactions that one can have in field theories, and why we're interested in certain types of interactions and not others. In particular, what I'm going to spend at least a little bit of time doing is talking about gauge theories and how we think of electromagnetism in terms of symmetries, and how that allows us to understand the construction of theories of charged particles. So these are, of course, so for example, this is the principle that we'll use to construct the theory of quantum electrodynamics. Okay? We're sort of 90% of the way there. We've already constructed most of the ingredients of quantum electrodynamics in this class. All we need is the idea of a gauge principle to bring it all together. And of course, gauge principles are also incredibly useful in condensed matter physics. So for example, along the way, we'll understand a little bit about symmetry breaking and superconductors. And so after probably about a week of discussion of the gauge principle and how we construct theories of interactions with charged particles, we'll go on and set up the machinery for studying these interactions. So we'll understand the machinery of Feynman diagrams. We'll use the language of path integrals to do that. That'll probably take a week or two for a scalar field before we finally get to the full glory of Feynman diagrams and quantum electrodynamics. And then we'll do as many computations as we can. Good. Are there any questions before we continue, or before we conclude? Good. Okay, great. See you guys all next week.